Hi, my name is Amanda Pound, and this is my ECE 303 presentation on lasers. To begin, I want to explain how laser light is different from ordinary light. Laser light is monochrome, meaning it only exhibits one color, whereas regular white light is actually a combination of all the visible colors on the light spectrum. Laser light is also directional, so this means wherever you point the laser, all of the light from the source will end up where you're pointing. Whereas with a regular, light bulb source of light, it emits from every direction. Laser light is also coherent. This means that it's made up of one uniform wavelength of light, so that's why a green laser will only be made up of green wavelength, whereas a regular light source could be made up of a multitude of different light wavelengths. The actual word laser is an acronym for light amplification by stimulated emission of radiation, and to unpack this whole title, we'll have to get into how lasers are actually made. To explain lasers, we have to start at the atomic level. Every atom or molecule that goes into a material is going to have a set of quantized energy levels. So if you think back to chemistry, these are the orbitals that surround the nucleus of an atom. If you add energy to the atom system, then through heat or light or other means, then you excite the atom. An atom is excited when its electrons jump to higher energy levels than their default ground state. The process of exciting these atoms is called pumping. When an excited electron eventually starts to lose energy and goes back to its ground state, it emits a photon, and this is called spontaneous emission. In lasers, these newly released photons can come in contact with other excited electrons and cause a chain reaction and make them emit as well. This is stimulated emission. When an electron is stimulated by a photon, it's actually going to release a photon of the same wavelength and phase as the original. This emission process is then amplified using reflection. Two mirrors, one perfectly reflecting and one partially reflecting, will be placed facing each other inside of a container filled with these atoms. The mirrors then help reflect the photons back into the container, causing even more stimulated emissions through chain reaction. Some of the photons then will eventually pass through the partially reflecting mirror. This is what creates the beam of light we think of when we think of lasers. All of the mechanics that make lasers possible come from the material that we covered in the very last chapter, chapter 8 of the course, as well as the material that we covered at the very beginning, specifically transmission lines, which are considered electromagnetic waves analogs, as well as how EM waves behave at boundaries, specifically the properties of reflection and transmittance. Lasers play a big role in our everyday lives. For example, in the medical field, lasers are responsible for a lot of eye surgery, whether it's cataract surgery or corrective LASIK. They're also used for cauterizing open wounds as well as precision cutting during surgery. Lasers can also be used for welding and cutting metal in factory production lines. Lasers can also be found in surveying equipment that is used to measure landscapes on construction sites. And lastly, they can be found in fiber optic cables, which we use for communication, such as the internet. In summary, I went over the properties that make lasers different from regular light. I then went into how these lasers work and how you might be able to fabricate a basic laser. Then I related this back to some of the course material that we covered in 303, specifically at the very beginning in Chapter 8, and then I went over some everyday applications for lasers. That concludes my presentation. I have also included a list of references. Thanks for listening.